Welcome to EDU World Space.
Let's calculate the change in enthalpy, the change in entropy, and the change of Gibbs free energy for a series of chemical reactions. The equations to be used in each of these cases is shown already. So to calculate the enthalpy of reaction under standard conditions, that's what that little zero or naught sign is about, we do that by summing up, that's what the sigma sign means, the number of moles of a substance times its enthalpy of formation for the product side. And then we do the same thing for the reactant side and subtract the two values. We do the same thing for entropy, and we do the same thing for Gibbs free energy. The N and the M in the equations deal with, in both cases, number of moles. We don't use N in each case just to make sure that you understand that the number on both sides may not be the same. Where do you come up with these H's of formation or these S's or these G's of formation? Those can be found in a table of values. Some that you might not find in a table of values are elements found in their natural state. And for those, you should know that the delta H of formation under standard conditions for those elements is 0. So you may not find them in the table. It's assumed that you know that they're 0. Entropies for elements do not have to be 0, so you do have to look those up. Okay, so let's start out with this first equation. We have hydrogen in its natural state plus fluorine in its natural state react to become hydrofluoric acid. And so we're going to use our top equation to figure out the enthalpy change during this reaction. Okay, so when we sum things up, what that means is we would add up all of the substances on that particular side of the reaction. So if you can see here, we have to look at the product side first. So we're going to look at the HF side. And we need to know the enthalpy of formation for HF. When you go look that up, you'll find it's negative 268.61 kilojoules per mole. And so what we do now is N is the number of moles. So we have 2 moles times the HF, which is negative 268.81 kilojoules per mole. Now, if we had any other substances, we would add those to this. That's what the sigma means, but this is the only substance on the product side. So we're done with the product side. We have a subtraction. And now we're going to go take a look at the reactant side. Now, the reactant side has 1 mole of each substance. These are elements in their natural state, so the delta H is going to be 0 for those. But let me just show you how this would be set up. There's 1 mole of H2. Now we know that the delta H for this is 0 kilojoules per mole. But what we have to do now, sigma means to add up. We have to do the same thing with the F2. And there's 1 mole of F2. It is also 0 kilojoules per mole. And that is our last substance. So now we would go forth and do the math and find that the delta H of reaction at standard conditions is negative 537.22 kilojoules per mole. Now we're going to have to do the same thing with the delta S of reaction. Remember, delta S is not going to be 0 for elements, but we were going to wind up doing this the same way. You're going to have to go look up those values. And so we're going to have 2 moles 173.51 joules per mole Kelvin is the value for that. That's the only one on that side. Now we're going to do the same thing on the reactant side. We're going to look those values up. And for the H2, we're going to get 130.58 joules per mole Kelvin. And then we'll do the same thing for the F2, which is going to be 202.7 joules per mole Kelvin. And we're going to get a value of 13.7 joules per Kelvin. And we'll do the same thing with the Gibbs free energy. We'll go look those values up. Again, remember that for Gibbs free energy, the Gibbs free energy of formation for elements is 0. And we'll go ahead and plug those values in. And we'll have our 2 moles times negative 270.70 kilojoules per mole. We'll do the same thing for the reactant side. And we wind up with negative 541.40 kilojoules per mole. The other problems can be done in a similar fashion. So this next problem, we have carbon with 2 chlorines in their natural state to make CCl4. And again, we're going to look up all of the values, but the process is the same. So we're going to take a look at the product side first. And then we're going to take a look at the reactant side. Both of these are elements in their natural state, so the delta H is 0. We're summing up each of the substances on each side. And then we add everything up. The delta S and the delta G are done the same way. To wind up with a value of the change in entropy of reaction for this system as negative 142.2 joules per Kelvin. And we can do the same thing with the delta G of reaction, looking up those values and solving. to wind up with a value of the delta G for this reaction of negative 64.0 kilojoules. We can also take a look at a third example where we have two PCl3s as a gas plus oxygen gas, which is an element in its normal state, forms two POCl3s. The math is exactly the same as in the last two examples, and you can see the work shown here and the answers to the correct number of significant figures. And in a fourth example, we have methanol and hydrogen in its natural state going to ethane and water as a gas. The process works exactly the same. We take the product side on the left, the reactant side on the right of the equations, and we multiply each of their respective standard values by the number of moles that they have.